Okay, today talk about crystals, fractures, and cleavage. I'm going to attempt to keep these videos from this point forward around 10 minutes. The last one was way too long, but it was an inclusive video. It included 2 of your questions in your book instead of just 1. It included number 4, which is how do we identify minerals, and number 5, what are some ways to identify those minerals. So that was in the last episode. But from this point forward, I'm going to try to keep it simple. And I've already kind of talked about crystals, fracture, and cleavage, so it should go a lot quicker. What you see right here is the definition of what a crystal is. I'm not going to sit there and read it verbatim. You can stop the video if you need to. But crystals are a reflection of the internal structure of the chemical compounds that make them up. So you start packing a bunch of molecules together, they'll bond at certain points, and then they will form certain shapes. And as you pack more and more together, of course, we cannot see individual elements or chemical compounds, but their stacking, their arrangements can be reflected in the larger structure. In the case of isometric, also sometimes called cubic crystal system, which I don't like this word and I'll touch on as to why that is, you can get a shape like this. Now, remember, I said there are 6 or 7 crystal systems, and they are defined primarily by their axes and angle relationships of those axes. That sounds complicated, but I'm just going to stick with the axes right now. In geometry and other subjects, you may see a graph, and you'll see something with an X and Y coordinate system. This is 2 dimensions. Well, cubes are 3-dimensional objects, and any other shape in nature. We live in a 3-dimensional universe of space, one of time, but we're just dealing with the 3 dimensions of space here. So you have your X and your Y, but there's a third, that's your Z, all right? So it comes out at 90-degree angles from your X and your Y. And usually in mineralogy and crystallography, which are very complex subjects, your X is often called your A, your Y is called your B, and your Z is called your C. So here's your A, B, and C, X, Y, and Z. How's that reflected in this? Well, this is the simplest crystal system because my X coordinate, now remember, I'm trying to represent 3 dimensions on a 2-dimensional surface. So your X would go from crystal face to crystal face. This is your X or your A. Your Y or your B would go from the front of the forward face to the front of the back crystal face, and that would be your B. Your Z or C is this axis. And in the case of isometric crystals, the length of these axes are all equal to one another. I'm not going to go into what the other crystal systems are. I can show it to you. Sometimes people will call these different things. Like this will be A1, A2, A3, but it's all the same stuff. So your A is equal to your B is equal to your C. In other systems, it might not be that way. Your A and B may not be equal, or in some, none of them are equal, or in other ones, A is equal to B but not equal to C, etc., etc. And some crystal systems will have lengths that are exactly the same as the others, but their angle relationships is what actually defines them as well, not just this. But I think that's all I'm going to say about that before it gets too complex. The reason why I prefer the term isometric to cubic is because you can be in the isometric system and not be a cube. Pyrite often forms cubes. Fluorite, which is also isometric, often does not form cubes. Well, if my A is equal to my B is equal to my C, how can I have a shape like this? Well, first I need to talk about crystal facies. Minerals are defined by the length of their axes and angular relationships therein. They are not defined by the superficial facies. and they are always the simplest crystal system they can be. So in a case like this, you see I've done this here to this cube. I've taken the cube and I've knocked off some corners. Well, I can keep knocking off corners through and through, more and more. And as you can see, the shape is going to change, but my A, B, and C relationships have not changed. So something like this is still isometric. I take this, all right, and the simplest crystal system I can put it in is isometric. My A length, which runs through here to here, this edge to this edge, A is equal to B is equal to C. Now, minerals can cleave and mess with this, and we'll get into that in a little bit. I've already talked about cleavage in episode 4, so I'm not going to go into too much detail or depth. But cleavage is how a mineral breaks cleanly, neatly, and not all minerals do. And some minerals can cleave along multiple facies or planes, if you will. And we'll just take our simple isometric crystal here. Now say this likes to cleave in one direction. We'll just say it's along our C axis. So it would cleave like this. And if that happened, so I hit this with a hammer, cleaves into 2. I hit each of these, and let's say it actually has 2 directions of perfect cleavage. So now I have 4 isometric cubes formed from 2 perfect directions of cleavage that are 90 degrees from one another. That's as in-depth as I'm going to get into that. All you need to know is that cleavage is just when a mineral prefers to fail or break along a planar surface neatly. So real quick about fracture, and I've already touched on this also in the previous episode. Fracture is just when things randomly fail, but patterns can form. Okay, so here's my isometric crystal again. I hit that with a hammer. Point of impact. It just radiates out. The breaks cross my A, B, C axes and just kind of ignore crystal facies and just cut across following the borders of the chemical compounds. This is still a mechanical break. You're not altering it chemically at all. And from the previous lecture, several things can happen here. The first main thing, you can end up with a random pile of just broken pieces strewn everywhere. The second thing that can happen, you can end up with conchoidal fractures. This would be where you hit that crystal, and instead of shattering into a million pieces, big chunk came off, and you see these ribbed structures spreading out from the point of impact. And on the scale of a rock, because these fractures happen in rocks too, we would call this a joint. Talk for another time. But there's your conchoidal, and then the third thing can happen. Instead of shattering when you hit it, or forming a nice set of rings in conchoidal fracturing, you just get a bunch of semi-structured breaks. And it could look something like that if you laid them all next to one another. Now, of course, there's all kinds of other cleavages and fracture patterns that can form, but this is a basic introductory course. And I hope you guys are really getting something out of this. And I hope it's keeping your interest, because as you can see, I really love geology, and I have my whole life. I never changed my major in college. I always knew it was what I wanted to do. We'll go deeper into my backstory some other time anyway. I think that's it for now, and I hope you guys did learn something.